Hello and welcome to the second in our series of Spatial Awareness Hangouts. This month we're going to talk about cosmology. I'm joined, as ever, Chris Lintott's here. Hello, Chris.
Hello.
And this month we're joined by Professor Andrew Jaffe from Imperial College London, who looks like he's speaking from the comfort of his own home.
Yes. Somebody's home, anyway. It's not clear that it's Andrew's from the picture.
It is in fact my home, yes.
And between us, we're going to try and unravel the current state of cosmology and what we know, and I guess to some extent what we don't know, or to a large extent what we don't know about cosmology. Chris, just before we went on air, you described it as being a mess, in that we don't know. There's a lot we don't know about cosmology, but there's one thing that most cosmologists settle on, and that's the fact that there was this Big Bang at the start of the universe. So. Andrew, the evidence for the Big Bang has been around for several decades now, the firm evidence. There's really no doubting that sort of central pillar of cosmology, right?
That's right. So what does the Big Bang mean? The Big Bang means that the universe is expanding over time, and that in the past it was denser, more stuff was crammed into a smaller space than today. And we see just so much evidence that those two things have to be happening. We see the expansion just by looking around us. Everything we see is moving away from us, and that would be true for any observer in the universe, so the universe as a whole is expanding. And we also see that if we look back in time, there is strong evidence, and of course looking further away is looking back in time, that the universe was denser, and if you look further back in time, actually much hotter than it is today. So we can get some evidence about the state of the universe in its much early times by doing cosmology.
And this looking back in time is in astronomy we tend to hail this as being one of the big advantages in astronomy, that we have a time machine that we can see backwards and see what was going on billions of years ago. But I've always kind of seen it as it's a blessing and a curse as well, because what we'd really like to do is be able to look at the universe around us today on enormous scales, on scales of billions of light years, and we simply can't do that. Because if we look at something that's billions of light years away, we see it as it was billions of years ago, and that makes things difficult.
Well, it's why we have to have this assumption called the cosmological principle, which is at the fundamental heart of all of this, which is the assumption that our little local bit of the universe is typical. Typical, maybe not in time, but certainly in space, and that therefore one can extrapolate that. That is an assumption. Finding ways to test that. As Andrew points out, the Big Bang for which we have evidence is the idea that there was this hot, dense state of the universe. Of course, there's rampant speculation, all sorts of fun scientific ideas about what might have come before that. But the history of cosmology in our universe, at least, starts a tiny fraction of a second after whatever the Big Bang itself actually was.
That's right. I mean, we can test that cosmological assumption, or sometimes called the Copernican assumption, after Copernicus, who was one of the first to show that we don't live in a very special place in the center of things. And we can at least test that things look typical wherever you are, that if you look in one part of the sky, they're the same as the other part of the sky. And of course, you can arrange things such that things are very delicately symmetrical around us, but that is so bizarre and so hard to arrange that you'd be able to see very, very small deviations from that, and we don't see that. So it's very hard to for us to be in a universe in which things aren't relatively homogeneous and isotropic on large scales. Those are the words that basically mean we live in a typical place in space, and that everything is more or less the same no matter where you might be in the universe. And we can test those to some extent, and we can test them by looking all around at a given distance, because at a given distance you're looking at the same time, and you can see that things are roughly the same at any given distance. So by looking at those things, especially at the very, very largest distances from us, and I'm sure we'll get around to talking about the furthest measurements we can make of something called the cosmic microwave background radiation, which is stuff that is almost the whole 14 billion years back towards the beginning of time, and that looks almost exactly the same temperature, or almost exactly the same stuff in every direction that we look from that at that very early time.
I think we probably should talk about CMB. If you only had one observation to take cosmologically, that's what you'd go for. Discovered more than 50 years ago now. This is radiation from a time, 380,000, 400,000 years after the Big Bang itself. And it's from a time when that universe was hot. So, Andrew, why do we see this radiation from that particular time?
So it turns out that this 380,000 years after the Big Bang was when the universe went from being opaque to photons, that is to say to light, from being opaque to light to being transparent. So just like if you look out, let's see, at least where I am in London today, there are clouds in the sky, and if you look at the cloud, you're looking at a surface. Inside the cloud, things are opaque to light, more or less. Light bounces around. But on our side of the cloud, then things are transparent, so the light just streams right through. So by looking at the surface of a cloud, you're seeing evidence of the light that some of it is bounced off the cloud from our side, but lots of it has come from the sun, which of course is on the other side of the cloud. And that's what we'd look at in the early universe. We see a cloud that's all around us, but it's 14 billion light years away or so, depending on exactly the way you count those light years. And by looking at that surface, we can get some evidence about the light that filters through that cloud and streams eventually to us over the intervening 14 billion years.
And so what is the key signs that we get from the CMB? One of the things we see is that the universe back then wasn't completely smooth.
That's right. It was nearly smooth. Things are roughly 2.7 degrees above absolute zero, almost everywhere. But if you subtract off that average, then we find that there are tiny fluctuations, about 1 part in 100,000, on top of that. And I think you're now seeing, if you're looking at the video here, you're seeing a picture of those fluctuations as reconstructed by the Planck satellite, which was launched by the European Space Agency in 2009, and which has been coming out with results, especially some very important cosmological results about 1.5 years ago. And that's where this picture is made from. So this egg-shaped picture, I should explain, is the surface of the sky unwrapped. So it's basically a map. You can think of the sky as a sphere just like the globe of the Earth, and you can unwrap that to make a map. And we just choose a particular way of making the map. Instead of making it a square, we make it an oval shape because that has certain nice mathematical properties. But this picture is just a picture of the surface of the sky, and you can see bits that are a little bit redder and a little bit bluer, and those are meaning a little bit hotter and a little bit colder. And again, a little bit is only 1 part in 100,000 or so hotter or colder. So very, very nearly exactly the same temperature, just 2.70001 or 2.69999 degrees Kelvin, and our very sensitive instruments are able to see that tiny, tiny difference and look at those fluctuations, we call them, on that surface 14 billion or so light years away.
So that tells us that the universe had structure. From those structures, we grew clusters of galaxies and everything we see today. But we can also look at how the passage of the microwave background light through the universe has affected it, and that can tell us about what's happened to the universe in the nearly 14 billion years since it was emitted. So Chris, you've worked on experiments to do this sort of thing. So what do we find out, and how do we do this?
Well, one of again, it's another one of these blessings and curses, that if we look at the cosmic microwave background, the light we're seeing has been traveling for 14 billion years, and it's traveled past or through everything in the universe between us and those very distant points. That is a pain, because we've got to somehow understand which bits of light we're seeing are from those early times and which bits are from stuff that's essentially, we call it, in the foreground, that's between those points and us. But also there's the really subtle effects that the mass in the universe has on that light. So as light can be bent, it normally travels in a straight line, but it can be bent slightly by the effect of mass. And as that light from the cosmic microwave background has traveled through the universe, it's been deflected ever so slightly. And we can see those tiny deflections when we study the map in great detail, and actually get a handle on how much stuff there is in the universe. We can kind of weigh the universe, weigh the density of the universe. That's one of the big things in understanding the structure in the universe, but also in as a total how much stuff there is in the universe. And it's been shown to be a lot more than we thought it was. So I mean, Andrew, the idea of there being stuff in the universe has been around for a long time. Since the 1920s, Hubble showed that the universe was expanding, as we discussed earlier. But the rate of expansion, the amount of stuff, our ideas of that have changed hugely over the past 90 years.
That's right. So if you just do a simple census of the stuff in the universe, so how would you do that? Well, you look out in the sky and you look at all the stuff that glows, because that's the stuff you can see. So nearby, the stuff that glows is mostly nearby stars in the Milky Way galaxy, and you can look beyond that and see distant galaxies outside of our own. And it turns out if you do that census, then the amount of mass that you can see by doing that is much, much less than the amount that seems to be necessary to account for the kinds of measurements that you talk about, which try to look at just the amount of stuff that has gravity. And you can see that on various scales. We can see within our galaxy there seems to be more matter than is gravitating, and on slightly larger scales of galaxies we see that, and in between galaxies things are moving a bit faster. So the galaxies themselves seem to weigh more than the stars and even the gas that we can account for in them. So we've postulated the existence of something that, for lack of a better term and for lack of imagination, we just call dark matter.
Because it's matter that's dark. It doesn't interact with matter. It has gravity. Dark. It doesn't interact with light. So it really does do what it says on the tin.
Yeah.
And we know a bit more about it, right? We know we often talk, though this is slightly more controversial, about cold dark matter, right? Which means that this stuff can clump together. It's not moving so quickly that it's just a sea of particles boiling all over the place.
That's right, and we have evidence for that because we see that the galaxies and clusters of galaxies are fairly heavy. So this stuff has settled into the gravity of these big, big objects. And so you can weigh them and you can see the ratio between the stuff that's glowing and the other stuff. And we have some evidence for how much of the matter, therefore, has to be moving relatively slowly. And so we call that stuff cold dark matter, as you said. And so we have pretty good evidence that most of the dark matter is cold. It could be a little bit warm, but basically it has to be cold enough to settle into what's called gravitational potential wells.
To allow galaxies to form, essentially.
That's right. If you had, there was a pretty well motivated theory that was around 40 or 50 years ago, which is that the dark matter wasn't cold, but it was hot. And the reason we had that theory was we actually know of some particles that might exist in the universe that could be the dark matter and must move around very quickly because they're so light, and those are the infamous neutrinos. And the problem is that if you had these neutrinos, they would be so light that they would never clump. They would never form galaxies and clusters of galaxies, and in fact they would deter the formation of them. So the universe would be much smoother than the one we actually see around us. And so we've been able to prove that the dark matter has to be cold, basically, in order to look like the universe that we see around us.
So if we think of this as a state of the universe report, so we've got dark matter, we've got this problem that most of the matter in the universe is a form we don't understand. How are we doing on experiments or observations to actually find out what dark matter is? It would be wonderful. I don't know why this matters to me so much, but it would be wonderful to know what the universe was made of. People are trying to do different sorts of experiments. People are looking for dark matter coming from space and trying to catch it as it interacts through, or catches interaction as it goes through Earth. But there's also the Large Hadron Collider at CERN, which may shed some light. So what's the latest news on that front?
Well, it's all pretty grim actually at the moment. So the kinds of experiments that look directly for, basically we're moving through the dark matter, so there should be a wind of dark matter through which the Earth and all the things on it are moving, and we look for the very, very rare interactions that those dark matter particles might have with the normal particles of matter, because even though it supposedly has very weak interactions with the normal, we call them standard model particles, protons and neutrons, electrons, stuff like that, they should, in any reasonable theory, have some way of interacting with that stuff. And so we look for those very rare interactions, and we have some particular theories for what kinds of particles these might be. For example, we think that if the universe is described by something called supersymmetry, which our colleagues at places like CERN, and in fact at the moment our colleagues in CERN and pretty much nowhere else on the world are looking for, and they're looking for it through just smashing normal particles together and hoping that some of these supersymmetry particles pop out. But if you have the supersymmetry, then that predicts that there should be something that has most of the properties of the dark matter. Now, the problem is we don't know if it actually is the dark matter, even if supersymmetry does exist. So we're looking in these ground-based experiments, these basically big vats of material that are very, very cold and very, very isolated. We're looking for very rare times when they get struck by something from outside that has managed to pass through miles of Earth and shielding and things like that, and finally left some trace inside these big vats of gallium and things like that. I don't remember exactly what kinds of materials they use. I think xenon is the most popular one nowadays. To date, we haven't found any very strong evidence for that. There are some, it must be said, there are some experiments that seem to have some tenuous evidence for these. Some people think these are not the most well-controlled experiments out there, so there's some controversy, and in particular, these results contradict, at least in the simplest models, the results of other experiments. So there's
I was going to say, it is true that if all the experiments were well controlled and knew exactly what they were doing, they should all be, and this signal was real, they should all be finding it.
Yes, so some of them aren't and some of them are, so that means that either the theory that you need to interpret the experiments is wrong, and that could also be the case, because they're not measuring exactly the same quantities. But if if the theory is correct, then one or more of the experiments, possibly all of them, are incorrect. And there are some ideas for relatively prosaic things that these detections could be seeing that might actually be an explanation for what they're seeing, but the jury is still out.
It's something we're almost not used to in astronomy, right? So much of astronomy is from observations that see something weird, unexpected, and then the theorists go and figure out what explains that, what theory could possibly explain those observations that have been made. And this is almost, although the idea of there being this dark matter came from observations, as we said, from way back in the 1930s initially, the idea of these weakly interacting particles in astronomical terms is certainly kind of treated as a theory. We're then trying to find observations that match. It's almost the other way around, the way we're used to doing things.
Yeah. Yeah, that's
but what about the LHC, Chris? Because we should mention that too, because the other option is to produce something that might at least be a candidate for dark matter.
Right, and so far... Yeah. Oh, go ahead, Chris.
Well, I was going to say, so they're currently upgrading the LHC to produce higher and higher energies to be able to produce these incredibly... Well, they're very massive compared to most particles we're used to. So when that comes online is it next year, I think it's due to come back online? That hopefully then sometime after that there might be some indications of what they've seen, but that's also these interactions are probably so rare that they have to get a lot of data before they can pick out the results. And as Andrew said, whether that then agrees with what all these other experiments have done, or whether we need to go back to the drawing board and think up more weird theories of what this stuff is, who knows?
Yeah, the LHC is unlikely to be able to see the dark matter itself or produce the dark matter itself, but it could produce other things that would give evidence that this general theory that there is dark matter of a particular flavor would give evidence for that.
What makes it unlikely to produce the dark matter itself? Is it that the particles are too massive, so you'd need too much energy?
Yeah, I think that and the cross sections, the ability, you produce other things much more easily than you produce these things in these theories, almost by definition, because these are very weakly interacting particles.
So I'm quite tempted to ask a meta question, Andrew, which is that as a working cosmologist, does it matter that we don't know what dark matter is? We know how it behaves. If your goal is to try and understand the universe, is it a first order problem, or are we happy with the state of the universe in which we just write down that there's this much mass?
I think it is. It's a first order problem because the effort of a lot of good people is spent worrying about what it is, and if the idea is right. So there's, we fairly confidently state that it is the case that there is this dark matter, but there are other ideas to produce one or more of the observational consequences that have led us to believe in the dark matter. There are other ideas to produce it. Now, most of those ideas have some fatal flaw somewhere, but some of them still hang around, and people really want to be sure, because it is so weird that we live in a universe that we see such a small fraction of, that people want to simplify, and it's much simpler to say yes, everything you see is what you actually have out there, and there's some other explanation for the movements of things.
It almost breaks that Copernican principle we were talking about, because we're suddenly a special component of the universe, right? We're made. I mean, there are good reasons to believe that we couldn't be dark matter people walking around, but there's something odd about the fact that we're made of a tiny proportion of the universe.
Well, we're special, but rare. So it's sort of, it's both Copernican in the sense that we're not at the center of things, because we are not what most of the things are, but it is special because it happens to be the stuff that has the right properties to be us.
Sure.
But on the other hand, if it didn't have those properties, we wouldn't be able to be us and see us and tell that we're here. And we could get into the so-called anthropic principle, but I think that's probably
let's continue reviewing the universe. So we've got a universe with more stuff than we can see, but we now know that accounts for only a proportion of the total energy budget of the universe. If we switch from just caring about matter to thinking about where the energy goes, I still the most shocking discovery of the last 30 years is that we live in a universe in which most of the energy now goes into an acceleration of the expansion of the universe, something that we call, much to my disgust, dark energy, by analogy to dark matter. But Chris, do you want to talk a bit first about how dark energy, how we know the dark energy is there, and then Andrew, maybe I'd quite like to hear from you about how novel an idea that was, and what it changes about the universe.
Well, I think the evidence that there is something called dark energy kind of came from two fronts at roughly the same times. In the late 1990s, some astronomers looking at distant supernovae, so exploding stars, figured they could look at these stars, see how fast they appeared to be moving away from us, which tells us how much the universe has expanded since that light left those explosions, and compare that with how far away they are. You can essentially, by measuring the brightness of those particular kinds of supernovae, you can get an estimate of how many light years it is to them, and then by doing that, you can compare the expansion rate of the universe over time. And what was discovered was that the initial experiments showed that it looks like the expansion of the universe, instead of getting gradually slower and slower and slower, as one might expect, is actually getting faster now. So it used to be slowing down, and it suddenly started accelerating in the last few billion years, is what the evidence has shown. And at about the same time, a few years later, some measurements from various experiments looking at the cosmic microwave background showed that if you look at the properties of those splodgers we saw, those red and blue splodgers, if you look at the size of those on the sky and compare that with the models of the universe, that says that the total amount of stuff, the total amount of energy in the universe is something like 3 or 4 times higher than the stuff we can account for, even assuming dark matter's there. So we're missing this 2/3 of the universe if we only account for the matter itself. And that really, the two theories do match. There's this sort of anti-gravity force almost that's pushing everything apart. That's a poor explanation for it, because there's not really any good analogies. But it really kind of it caught a lot of attention when it was discovered, and there are no analogies for it, are there, Andrew? It's a really confusing thing to try and explain.
Yeah, it's sort of just, and it's a form of anti-gravity, but not in the sense that you'd want to build jetpacks out of or something like that. It only works on large scales, and it just has this bizarre effect that it tends to push things apart on very large scales when things are not able to be pulled together by their own local gravity. And the dark energy does exist here. It is a slight counterbalance to our being pulled to the Earth by the gravity of the Earth, and on our being pulled around to the Sun as we move around the Sun. But it's so much weaker on these small, relatively small scales that it has absolutely no effect. I want to point out that that although the two lines of evidence that you have given are far and away the most compelling, in fact, there's always for a long time, even before the late 1990s. There was I think the current popular way of describing this is a tension, a tension, not a tension, in cosmology between various measurements. In particular, the age of the universe. We had a pretty good limit on the age of the universe because we have a pretty good idea of how old the oldest things we could see are. And
stars form pretty quickly, as far
yeah,
as
stars form quickly. And if we look at clusters of stars, all of whom are formed at the same time, we believe, and we have good evidence to test that, then it looks like there are clusters of stars that are 12 billion years old, at least. And if you look at how fast the universe seemed to be expanding nowadays, then in the universe that is only made up of even dark matter, then there wasn't enough time. So a universe with dark matter and that expansion rate today would have been only 8 billion years old. And
so we'd have stars that are older than the universe, which
exactly, and that's a contradiction, obviously. So people were already by the 1990s postulating that the universe must have some other component making it older. And I belabor the point because I wrote a paper on it, I admit, but which is, I think as good a reason to talk about it as any. But in fact, even before these famous supernova results that you discussed came out, there was already a paper, not by me, this one, on what is now called, and in fact what was first called in this paper, the concordance cosmology, because that's what you needed in order to explain all these disparate measurements, even that existed before the direct evidence for the accelerated expansion of the universe. So it's not a new idea, I think, which is one of the questions Chris asked me. It's really been part of cosmology, in fact, since the very beginning, and it's been part of the theory of gravity since Einstein came up with it. So very famously, this thing that we now at least can best describe by a term in Einstein's equations for general relativity called the cosmological constant, or capital Greek lambda, so an upside down V, basically, for people with Roman letters. So that was in his very first equations, and he had it in because he wanted that extra expansion, that pushing outward, to counterbalance the pushing inward of things, so he could have a universe that didn't evolve over time. Because when he first wrote down his equations, he thought the universe was not evolving over time because it was before Hubble's observations of the expansion. Once he found that, once he learned that, then of course he was happy to jettison those terms. But in fact, it was kept around, and people from the very beginning up until the 1990s, you'd never found a cosmology textbook that didn't at least acknowledge the possibility of this cosmological constant being part of the universe.
So, what is it?
Yeah, that's a very good question. If you thought it was embarrassing that we didn't know what the dark matter was, it's way more embarrassing that we don't know what the dark matter was. It's way more embarrassing that we don't know what the dark energy is. If you write down the simplest back-of-the-envelope calculation that you can do to predict what the dark energy, how much dark energy there should be in the universe, then you can come up with three numbers. But back of the envelope, the simplest number you can come up with.
Quantum effects, right, to do with properties of space and so on.
That's right. The simplest number you can come up with is 0. And that actually, it's very hard to come up with that number, but you could sort of believe that it might be the case. So we know that it's not 0 because we observe it out there pushing on the universe. The other number, so that when we measure it in the units that we generally use, the number that we measure for this stuff is about 0.7. Doesn't really matter what units that is.
But it's a fraction of the energy in the present day unit.
Yeah. So 70% or so is roughly this. If you write down this back-of-the-envelope calculation, the first number that you might come up with is a little bit higher than 70%, or 0.7. It's 1 followed by 60 zeros. And in fact, if you do the calculation in a slightly more naive way, it's even worse. It's 1 followed by 120 zeros. So we were very happy when we got rid of that those first 60 zeros, because we're only off by 60 orders of magnitude, as we call it.
Oh, I actually hadn't heard that. So well done.
Yes, that's by taking the supersymmetry into account. Turns out that would balance out some of the terms, but still 10 to the 60 is sort of embarrassingly large.
So what's the correct way to think about that? Is it that explanation is no good, and that we need a completely new explanation, or is it that there is some trick that we're missing to get rid of the other 60?
Yes, one of those two things might be correct.
Yeah.
So so one possibility is it's a back-of-the-envelope calculation. You kind of need to know quantum gravity to do the calculation correctly.
Which we don't.
The most famous thing in theoretical physics that we do not know is a theory that marries quantum mechanics and gravity, and so we kind of know from the outset that we don't know enough to really answer the question. So it could be that's just the back-of-the-envelope version is just wrong. It could be that it's right but misleading because there are other things that cancel it out somehow. Or something that people have become, this is the anthropic principle I mentioned a few minutes ago, something that comes up very often, is that actually it's chosen somehow randomly in the universe, because this is a quantum mechanical phenomenon after all, and quantum mechanics is all about randomness. And we just happen to live in the universe that picked out this number that it is. And the best argument for this was made actually by the very famous theoretical physicist Steven Weinberg in a paper in the late 1990s again, although written before this fairly strong evidence for the cosmological constant existed, where he pointed out that if it were much larger than about 0.7 or 1 or so, then it would hinder the creation of galaxies in a similar way to the hot dark matter that we talked about earlier in the broadcast.
You can sort of instinctively see that it would be hard to form galaxies in a very rapidly expanding universe.
Exactly. So things are pulling apart, and that is stronger than the pulling together of galaxy formation. So he noted that the highest number you could get away with would be about 1 or so. So 0.7 is about 1, so that's close enough for government work, or for cosmology more importantly. And that was importantly before these observations had been made, so it was in some sense a prediction, which is good. But you also need to say that it's going to be the largest number it could possibly be, and that's because the typical number is still 10 to the 60 in this idea, and it's just that for any other number, there's no way you would actually have a universe with observers like us to see it. So that is a possible explanation, and that's gotten a little more of a boost in the subsequent 2 decades as this idea from string theory called the landscape has come up, and that's a more specific mechanism for having a random process which chooses the constants that describe the universe. So again, we don't know if this is even remotely true. It could just be people making stuff up. But if not, then there is a way that you sort of have to flip a bunch of coins, and then figure out where you actually end up living. And because most of the time where you flip those coins, you'd not be able to produce anything like the universe that has our kind of life in it. So the only time you get to see a cosmological constant is when you get exactly the right coin flips, and you would expect to more often see one towards the large end than the small end, and that kind of gives us the universe that we see. It's not very satisfactory, to be honest, but it may be all we end up with.
Yeah, the other thing that's unsatisfactory about dark energy, of course, is that we don't have much information about it. We can measure its strength now, and there's an awful lot of effort and some very big surveys going into measuring whether that strength might be changing. But it would be perfectly consistent with everything we know for it just to be a constant force, or a constant, once you take into account the expansion of space. And Chris, that leaves us observers with very little to get our hands on to try and... Normally when you have a mystery like this, you want to observe it, find out lots of things about it, which will help the theorists narrow down the explanations. Here, it's very difficult to see what those observations might be.
Yeah, it's kind of in contrast to the dark matter, where we can have ideas about what it might be and then design experiments to go and test those ideas and those theories. With dark energy, we're left sort of drowning in well, not drowning. We have no idea what to do. We're just left struggling for tests to make, for tests to conduct to see what this stuff is. And as you say, there's lots of effort in looking for what the effect of dark energy is, whether it is getting stronger or weaker over time, maybe whether it seemed to be different in the early universe. We could perhaps tell something like that. Whether maybe it varies at different points. If you look at very, very distant parts of the universe, can we maybe see that it appears to be different over there? There are all sorts of things we could think about testing, but none of them come anywhere close to saying, well, what is it then? We're still left with what Andrew pointed out was a factor of 10 to the power 60 in our best ideas of what could be causing this. And as far as I'm aware, we're not, although there are some, well, Andrew said that the theories have some big unknowns, I don't know whether there's any way of getting in the near future, getting closer to figuring out what that is. I mean, is there any progress likely to be made? Do people think they're going to make progress, Andrew?
On the theoretical side or on the observational side?
The theoretical side initially. Isn't it?
It's pretty far from my wheelhouse, but I think there seem to be aspects of string theory, this vaunted idea for combining gravity and quantum mechanics, which does produce the kinds of dark energy that we want, at least some of the time. But again, because of this randomness that I talked about, we may not even learn anything from that. So on the theoretical side, it's a pretty big problem, and it's not clear that it's really solvable in lots of these theories.
So we're beginning to run out of time. We seem to have talked ourselves into a slightly depressing corner, in which it's exciting not to know things, but it's not as if either of us are pointing to specific experiments that will help us with dark energy or dark matter. So Andrew, where is the excitement in cosmology? Where is progress being made, and what should we look out for in the next few years?
Well, so I think I'll first talk about the microwave background, because that's what I spend a lot of my time doing. But I think there is progress to be made on the kinds of questions you've been talking about on the observational front. But in the microwave background, perhaps some of the listeners and viewers know about the Planck experiment, which is a big satellite launched by the European Space Agency in 2009, which I think we may have mentioned already before.
Yeah, you've credited ESA twice now, so you can relax.
Okay, and we had our first release of cosmological results in 2013, and that was looking at the picture that Chris put up before of the temperature of the microwave background everywhere. But it turns out that one of the other things you can measure from the microwave background is its polarization. So light isn't only a brightness, but it also has a little stick, which you know if you have polarized sunglasses, you can see by twisting them around and seeing how the picture changes. And the early universe, it turns out, produced polarized light for us, and that gives us essentially two more numbers we can measure at every point in the sky. And those numbers can tell us more information about the early universe, and they can both confirm the numbers that we've already measured, and they can also, we hope, give us more information, at least a few other pieces of cosmological information, such as, in particular, a lot of the stuff about the foregrounds that Chris mentioned along the line of sight. They have an effect on those polarized photons, and we can use that to disentangle some of the early universe effects from the late universe effects, which is one of the major prospects of this. But one of the other things that this polarization can do, and something that's been in the news over the last 6 months or so, is that if you look at those sticks that come attached to every point on the sky, you can make a certain kind of picture out of those sticks and sort of the swirly patterns that exist in them. And those are very hard to produce in the early universe except by ripples in space-time, so-called gravitational waves. Those ripples, we think, we can only have a couple of ways they can be produced. And really the easiest way to produce them is a phase in the early universe called inflation. And this inflation is just like this expansion, this rapid accelerated expansion we've been talking about in the late universe, except that it happens at, instead of 14 billion years after the Big Bang, it happens at 10 to the minus 35 seconds after the Big Bang, which is very, very early on indeed. And it lasts for long enough, however, even though it's only lasting for about 10 to the minus 35 seconds as well, that's long enough to take quantum mechanical small bits of the universe, so much, very, very subatomic things, and make them a little bit bigger, or make them quite a bit bigger in terms of the factor, but only sort of golf ball sized or something. But those golf ball sized bits of the universe are big enough that they've frozen in the quantum mechanical randomness from the early universe. And those, we hypothesize, are what's responsible for that modeled picture that we saw before, as well as these gravitational waves, the gravitational radiation that was responsible for this polarization. Now, the problem is that we have some conflicting evidence about this polarization, or about these gravitational waves anyway. So Planck has made a measurement of the gravitational waves through another channel, let's say, and by some measurement of this, we have this number r that we call, that we use to measure it, and Planck says that r should be less than about 0.1. But in March of this past year, a team of very, very careful, very, very good experimenters, mostly from the US, using an experiment called BICEP, which is an experiment at the South Pole, sort of a telescope looking up at the sky from there. They have evidence, using this polarization we talked about, that this number r, instead of being the less than 0.1 that Planck says it probably is about 0.2.
And as you said earlier, this is what we call a tension in modern parlance.
This is a tension. Other people might call it a disagreement. Some people might say that one or the other group is actually wrong. One of those things is probably true at the end of the day. And so what both the BICEP team and the Planck team are feverishly working, even as we speak. And in fact, the reason I'm at home is because I've come back from Cambridge, where I was at a Planck meeting for this week. We were trying to, among other things, work on our papers that are trying to duplicate some of the analysis that the BICEP team has done. In fact, some of the analysis is being done together. So we're talking to these other teams, and one of the things that has come up is the question of how much of what the BICEP team sees is really primordial. So
from these gravitational waves.
These gravitational waves from the microwave background produced 400,000 years after the Big Bang, and how much of it is essentially due to glowing stuff in our own galaxy.
From dust.
From dust, yes.
And
so
I have to say, as a local astronomer, if there is this much dust in our galaxy, then that creates an interesting problem. It's not as interesting, perhaps, as inflation, but working out how much dust there is and where it's distributed in our galaxy is a strong constraint on what we think we understand about stars right now.
That's right. I mean, even if they turn out to be wrong, the BICEP team are not stupid. They're very good experimenters, and they're good scientists. So they looked at the best extant models for this dust contamination that existed when they wrote their paper first, late last year and early this year, and all of those models said that they were not strongly affected by dust contamination. So they weren't, they did some amount of due diligence here, but it turns out that there is at least some evidence that those models may not be right. And we have reasons to believe why they might have made these sorts of mistakes, and the details of understanding that are trying to be worked through now. But you can find reasons why they might have made mistakes, but that doesn't take away from the very impressive technical achievement that they made.
And the review process really established that this does seem to be a real detection. It's just we're not sure what it's a real detection of.
That's right.
It's not an experimental error. It's not some screw up in the calculations or in how the telescope was set up. It's just that we don't yet understand what the source of this signal is.
That's right. And their experiment by design didn't have a way to tell the color of what they were seeing. So it turns out that the CMB, the microwave background, is essentially white whereas the dust is red. But they had no way to tell the difference. All they could tell was brightness in a particular band. And so they just had to go on these calculations that showed that the contamination couldn't be very large. Those calculations may turn out to be wrong.
Yeah.
Well, that's one of the big advantages that Planck will bring to this as well, right? Is that this different colors it can look at to really be able to tell the color of what's being seen. That's one of the big things it will bring to this discussion.
That's right. So Planck will be able to do an observation over both so Planck looks at the whole sky, whereas BICEP only looked at about 1% of the sky. So it's a very different kind of experiment. And it turns out that only over that 1% of the sky, Planck is not as sensitive as BICEP. So BICEP is even though Planck is a satellite, of course the way these things work is you build satellites with decade-old technology, whereas you put things on telescopes on the ground with the newest stuff you can build.
And BICEP's been upgraded many times, and is taking data again. So
that's right. So they are actually more sensitive than Planck, but of course Planck has more frequency coverage, as Chris mentioned. So those two things hopefully will mean that we can come up with a more definitive answer anyway over the coming months.
Good. Well, plenty to look forward to in all of cosmology, even if we don't know what the universe is made of. So, Andrew, thanks for joining us. Chris, you'll be back sometime towards the end of October talking about Rosetta's mission to Comet Churyumov-Gerasimenko. I'm not sure I can make it, so I wanted to get the pronunciation in now. And to all of you, thanks for joining us and for thinking about the universe on this Friday afternoon.
Thanks, guys.
Bye.
Bye.